getting bigger and bigger. Lipid cell or muscle cell becomes bigger. That's a hypertrophy. Trophy is a nutrient. So big is not becoming bigger. Hyper is the opposite way. 그래서 이렇게 쓰는 게 좀 좋을까요? Hypertrophy can be smaller. Hyperplasia becomes more numbers. If it's regular, then hyperplasia is kind of growth. Neoplasia is abnormal. New form and getting more numbers. It's neoplasia. That means usually neoplasia means breast cancer. 뭐들이? Alpha ray, and recently in Korea we have a new cancer therapy machine installed. 중입자 가속기 heavy ion therapy. What is the atom on that machine? Carbon. Carbon 12 is the atom, and the bigger it has a higher energy. You can cure the cancer in 2 minutes. You have cancer chunk, not blood cancer chunk, then you can shoot that heavy atom, then it can kill those cells in 2 minutes. Alpha particle is helium nucleus, right? The atomic weight wise is 4. Carbon 12. The bigger, the higher energy it has. X-ray, gamma ray, they are electromagnetic wave. Cosmic ray, even shorter wavelengths coming from far, far away the galaxy. That's a cosmic ray. Usually they say, if they are really particle, beta ray is a particle of, Jenny? Come on! 7. Beta ray is? Helium is alpha ray. Beta? Proton? No. Lighter. Electron. Beta ray is electron. Okay. So alpha, beta is a particle flow, high energy particles. The heavier, the higher energy. So for the therapy right now, the current therapy is when above alpha particle is carbon particle is kind of the choice for now. All others are electromagnetic wave. Okay. So-called light. First generation of anti-cancer drug is kind of destroying the chunk, right? Heavy atom, heavy ion accelerator is also kind of the chunk, the treatment. That's why hidden small cancer cannot attack. It should have a big one. Big one, the target is either DNA replication, or cell division. These are the so-called chemotherapy. And second generation, the topic we are going to learn today, that is for signaling part, not the whole army, not destroying the tanks. It's destroying their messengers and cut their signals. That's targeted cancer therapy. That's the second generation. Okay, that signal, that flow cytometry figure shows a typical DNA labeled signal. So this is a 2N, this is a 4N, and this is a G0, G1, S synthesis of DNA, not RNA. This is a G2N. So this is actively growing population. If it's not growing cells, what do you see? No growing. Okay. Still actively growing, still G2N population is relatively small. Majority of them is in G1. Okay, this is active growing cells. Not RNA, it's DNA, not antibodies, and this is dividing cells actively. Okay. If you inject your heart cells, take out your heart, segregate and inject, what do you see? You see this. Heart does not divide. That's why you never heard heart cancer. No divide, no cancer. Actively dividing, they have more chances to get cancer. Neuron, they don't divide. So there's no neuron cancer. The glioma, the brain tumor, they are glioma. That's astrocyte cancer, not neuron cancer. Okay? Only dividing cells can have a chance to go wrong and become cancers. That figure you have seen, what can you say? What is the character of this pattern? Which arrest? M-phase arrest, right? M-phase arrest. Then you can look up those drugs. Which one is the M-phase target? It's a Taxol. Taxol targeting microtubule. That's why this is the M-phase. Cisplatin binds to DNA. Topoisomerase is also inhibiting those DNA synthesis. Then that would be more S-phase. Then you expect more accumulated cells broadly here, not in base. Okay, that's how you can interpret those effect of those drug compounds, where it is attacking in cell cycle. Okay, kinase inhibitor is a signaling, so maybe you don't see much effect, maybe, or maybe slowly increasing here, stop here. It doesn't move to the next step, depending on the target site. Okay, 100% answer, but one did not answer. Signaling transduction is just through plasma membrane. That's the main issue. I will give you 10 seconds. By mistake, I gave 1 minute. Okay, inositol phosphate is the second messenger. And how about the calcium? Again, in 10 seconds. Okay, that's a third messenger, and we will see why. good. In cancer, they will uptake more glucose, more nutrients, and they will increase the lactate, you see, and DNA synthesis is increased. This part is not increased. That's in normal cells. Okay, so based on this, let's go to okay, today's topic is targeted cancer therapy, second generation of cancer drugs. And question was given by you. What is the second messenger? I understand the first messenger here, but why this is the second messenger, not these guys? Okay, that's a fair question. And this is what I gave you in the drawing. Maybe drawing was not good enough. The real drawing made like this. So first messenger is coming from outside, like a ligand. The ligand usually cannot penetrate the cell membrane. If it's a hydrophobic ligand, like a steroid, they can penetrate it directly and it can reach its target, most likely in the nucleus, the transcription factor. Then they don't need a second messenger. First messenger can reach its target, then that's it. But most of those the ligand or the signaling molecules, they are hydrophilic. They cannot penetrate the plasma membrane. That's why they need to transfer that signal into different form. So usually first thing is binding this ligand, first messenger bind to the receptor. This receptor itself can be enzyme, or it can transfer that signal to another machines. So in this case, this receptor, if it binds to the ligand, they change its shape. That change affects the configuration of this so-called G protein, and that change of G protein affects maybe another enzyme, and this enzyme all complexed together in the same area. And then this is the substrate of this enzyme, and this substrate is cleaved by this enzyme, and released molecule is this inositol trisphosphate. So then with this picture, we can see, okay, this is all working together as a machinery, but really released signal is this guy. Inositol trisphosphate is one sugar similar to glucose size with a 3-phosphate. So it's a kind of another hydrophilic molecule which cannot go out, but it can mobilize calcium inside the cells. So there's a calcium store inside the cell. Usually cytosolic calcium concentrations are nanomolar, very, very low. But this inositol phosphate binds to another receptor and releases calcium. Calcium usually acts as activating signaling molecule in many parts of the cell in our body. So that's why in this example, first messenger binds to the cell surface. If there's any material released, this is a clear area, right? This one, oops, sorry. This one is the second messenger. And if it generates another messenger, then third messenger. And why is that important? First messenger is a single molecule. And this enzyme can generate many IP3 with amplification. Again, one IP3 binds to receptor can release many calciums. It's a further amplification. Okay. That's why this whole signaling of the pathway is moving across this plasma membrane and generate another messengers, and then make the endo effect. So this is what we call signaling pathways, signal transduction, and cancer has its own signal transduction. And that signal, if we can attack, then it's different from killing the chunk of the cells. It's specifically shut down one signal. It's like a sniper to attack that target. That's a targeted cancer therapy. Potentially, it can have low toxicity and chemotherapy. Okay, what will be effect? So here, Hongju, you said this is not through citric acid cycle. Citric acid cycle is oxidative phosphorylation. What does it generate? Through this cycle, cancer cell not through this, and through this, what's the product? Normal cells use citric acid cycle. Through citric acid cycle, what happens? Phosphorylate where? Okay, she gave the keyword. End of this citric acid cycle is ATP production. By taking the glucose through glycolysis, it is breaking down 6 carbon sugar into 3 carbon sugar, 3 carbon material. And then one of them is a pyruvate. Pyruvate goes into citric acid cycle or TCA cycle. And then if that is fully disassembled, then that energy is converted into ATP production. If ATP is produced, about 20-30 ATP can be generated from one glucose. Cancer cells do not take that pathway. Cancer cells stop that reaction, does not put the pyruvate into this cycle. Instead of that energy production, it uses those materials to build up more body. Okay, that's what we effect. And Minseok says, nice story about lactate, pyruvate. So if the lactate dehydrogenase is important for cancer, then he said using siRNA attack lactate desensitase. How does it work? What is the mechanism for siRNA? What is siRNA? Prevent the translation of which genes translation? LDH dehydrogenase on which state? DNA, RNA, protein, mRNA. siRNA is attacking mRNA of this enzyme. Okay? That mechanism we are going to see today. So I asked you to choose one abnormal signaling. Okay, one of them is P53. P53 is apoptosis inducing important player. If that one has a problem, if my body has, I don't feel good, I may affect negatively to my friends. I may just commit suicide rather than affecting negatively. That's apoptosis. If that is wrong, then even though I don't feel good, I want to kill my friends or do something bad, still I don't die, then that's a problem. So that's apoptosis function. P53 is major player for apoptosis. If you hear P53, okay, P53 is a good guy. Because if anything goes wrong, then it blocks by suicide. If that goes wrong, then neoplasia can happen. Now, that pathway is also downstream somewhere there. Kinase somewhere. Let's see. Kinase is the usual activation pathways in our body. This is another one, PI3 kinase. And why kinase? What is the function of a kinase? Kinase is enzyme. Phosphorylation. Okay, the end result is a phosphorylation. Then, how does it work? Using what? It phosphorylates what? ATP. Another protein is always a protein. Then, if it's not protein, then what can be possible substrate? And in this signaling pathways, there are a lot of kinases involved. Kinase is a phosphorylate, more specifically, phosphate transferring enzyme from ATP to another target. It can be protein, it can be carbohydrate, it can be lipid, and many other materials. And phosphorylation is main mechanism of the signal transduction. We have seen inositol phosphate generation. Calcium is one pathway, but another big class of pathway is activating kinase pathways. Why kinase has been chosen, you think? If its target is a protein, introducing phosphate, what do you expect? One more hydrophilic, okay? It's a possible, it's a more hydrophilic and more energy, well, energy, okay? Let's do not count that part. And other part, more active. How do you define active? Energy, negative charges, and how is it connected to active? Stable, unstable because it has more energy. It is non-neutral. Okay. So if it is connected to the energy, then single phosphate does not have a very high energy. Triphosphate has high energy. That's why ATP can be used as energy source. But here, activated or neutral, well, if you think about in this level of a molecular level, the dominating force is out of 4 basic other forces in nature. Which force is dominating? Gravity? No. Strong nuclear power? Nuclear force? No. Weak nuclear force? No. And electromagnetic force, right? And electric force, if you look at, among what you know from the periodic table, up to third family, N, P, O, S, among them, which can generate the strongest change of charges? Ammonium +1, oxygen -1, sulfate -2 maximum, phosphate it can generate -3. Phosphate can generate the biggest changes of charges. So activate, inactivate is not clear, but at least one state, and then adding phosphate may generate maybe biggest change in terms of electric force. And it's optional, either adding or removal. And if you look at those signal transduction pathways, we have about 500 kinase. Opposite enzyme of removing phosphate, what do you call? Adding phosphate is a kinase. Removing phosphate, phosphatase is the enzyme to remove. And we have a 500 phosphatase, 500 kinase, and about 100 phosphatase. That implies that which one is the signaling activation pathways? 500. For activation, you don't want to have general effect. To come down, you can remove any phosphate. That's why we have a lot more kinase than phosphatase. So based on this, if you think, now here, one example, interesting example here, BCR-ABL, hearing. What does that mean? BCR-ABL. What is that BCR-ABL? 이거 네가 쓴 거 맞아? 홍준관도? Who wrote this one? Okay, good. BCR-ABL is
putting proton tyrosine settings.
it's also kinase. Then BCR-ABL, when does it happen? Cancer has a BCR-ABL overexpression.
Specific cancer form CML.
CML, chronic lymphoma.
The chromosome. There exists a very abnormal chromosome called the Philadelphia chromosome.
Okay, I'm happy to hear this example. BCR-ABL is a quite historically the important and also conceptually interesting topic. I said kinase is usually the target of abnormal signaling. So cancer may increase the activity of a specific kinase. That's one possibility. Another possibility was found here in BCR11 case. In this case, in cancer, there's a lot of mutation happens, and also this kind of exchange of part of the chromosome, so-called translocation, happens. When they translocate like this, and that junction part, one part was given by this, the other part is given by this, and this complex together, it generates active kinase. And this kind of abnormal exchanges, and then resulting resulting chromosome, and this chromosome is called the Philadelphia mutation, Philadelphia chromosome, and it is a kind of a marker for CML. So for some specific cancer, they have kind of preferred translocation, and then very interestingly, that junction, this red part and blue part meet together. One part is BCR, one part is ABL. They constitute active kinase. So very interesting example of how this becomes cancer. Because of that active kinase, that cell becomes cancer. And then very famous drug for this is this one, Gleevec. So you may have heard that name, which is a small molecule drug which attacks this one, almost a miracle drug in the beginning. It could cure almost 100% death of the CML. Okay. So this is the concept of the Philadelphia chromosome induced by translocation and generating the kinase, abnormal kinase activity is kind of a very interesting observation here. Okay, so today I said, kinase is kind of a very common target of signal activation. And overactivated signaling is usually the problem. So if you look at, so for example, cell cycle checkpoint, each point from starting from G1 going to S phase, whether to cross this or not, whether I start to the DNA synthesis or not, that's important the decision. Here there are checkpoints. Those checkpoints are kinases. And synthesis, after the synthesis is done, then G2, and then check everything again. Everything is okay to divide or not. There are a lot of kinases that are involved here. Those kinases, cyclin dependent kinase families, CDKs are one of those signaling out of 500 different kinases. CDKs are quite popular cancer targets. So kinase, let's think. Enzyme activity-wise, kinase is a transferring phosphate, and if this is kinase, and this is your bullet, then the bullet will be, the shape is like this, ATP. ATP triphosphate. If it is one phosphate, energetically it's not really active. Two phosphate a little, but that's not super active. Triphosphate now then becomes unstable. So transferring this phosphate to the target, then this target can be, this is your substrate of this kinase. So that's why this is kind of a phosphate transferring enzyme, is the kinase. Now, if you develop drug, if you want to if we know that this kinase is a problem, either it's overexpressed or new kinase is formed, like a BCR11, then we want to kill that kinase activity. What can you do? Okay, one way is make the similar shape of the substrate, and then it is bound to kinase, and then don't let this bullet shoot. And here, this bullet, this part is this part, and this part is this part, right? This is the transferring part. So one way is making those drugs similar to substrate. Substrate mimicking, because this kinase may recognize this part and then block it. That's one way. The other way maybe you can mimic this one. ATP-like material. then if that group binds loading part, ATP should bind here, and if you add ATP derivative, then it cannot load it here. That's another approach. ATP is another substrate, right? It's a cofactor, but anyway, kinase need to bind to ATP, and also it need to bind to substrate. Then it can be transferred, right? Or maybe it can bind to other part of kinase and change its conformation somehow, and then don't let the trigger. So this kind of a design is small molecule which can bind to kinase itself and mimicking substrate or mimicking ATP or binding to other important part and then don't let it move. So this is a usual design method of making kinase inhibitors. So this is a small molecule drug. There's other two approaches. How about physically breaking kinase? Previous one was that those small molecules, they are inhibiting their function, right? By putting those molecules and inhibit their function, if you choose breaking the kinase, how will you do? Junyoung, how will you break the kinase in the body?
Like the binding of enzyme and substrates. Bind something to kinase and change the form.
Sounds like that's a drug approach. Break the kinase itself. How can you break it? Okay, there is some protein degradation process in the body. To break the proteins, one way is utilizing protease enzyme. Protease enzyme recognizes some part and then cleave those parts specifically. But to do that, we need to have many proteases. So that's not so efficient. Another common approach is so-called ubiquitination. So if ubiquitin is added to the protein, then this ubiquitin is also kind of a small peptide, small protein, and that process is repeated. And ubiquitin added. So whoever you are, it doesn't matter. So I put those stickers to ubin, 1, 2, 3, 4, 5 stickers. Then another person is coming. Who has the sticker? And you come out. And then ubiquitinated protein is, regardless of what is this part, ubiquitin part is absorbed here, and everything is broken. So this kind of a degradation pathway is through proteasome. Protease is one enzyme. Proteasome is a kind of a big machine, big drum, and any material, I don't care, if you have a sticker of ubiquitin, then just take it and break it. In our body, DNA is the information part, protein is the machinery part. Making protein is a very important function. Which is the enzyme to make a protein? Jeona, what is the enzyme of making protein? That's a ribosome. That's not a protein enzyme. That's a RNA enzyme. Big chunk of RNA has the function of making protein. Destroying proteins is one way, one by one, but big chunk of those breaking protein machinery named as proteasome. And the signal is ubiquitination. Putting those sticker and kill it. Utilizing this mechanism, maybe you can break kinase. Then we can think how the ubiquitin is added. Ubiquitin is also utilizing ATP and then transferred to E1, another enzyme. And then this E1 is loaded like this, and then E3 is utilizing this complex as a cofactor. and then transfer this ubiquitin to the target. So similar to kinase, right? Kinase is loaded ATP here and then shoot those phosphates to the target. Ubiquitin labeling enzyme is called as E1, E2, E3 are the complex. E3 is the most important to recognize this substrate and transfer ubiquitin. And usually this is a little far away, so you need to have some connector in between. And E3 and then substrate should be close enough to each other. Then ubiquitination can happen. So the whole process is like this. Activated ubiquitin is binded to E3. And there is this linker is connect this substrate to E3. And then if when they are close, ubiquitin transfer to substrate. And then this step can be repeated. Then this target is ubiquitinated. Once they are ubiquitinated, then they can be destroyed by proteasome. Here, if you look at carefully, this is natural system. This is your target. And this is something you can add from outside. And after this is broken, this can be released. It can be recycled. In kinase inhibitor, if you add a drug to suppress the function of a kinase, anyway, that drug should bind to somewhere, right? To the substrate binding site, ATP binding site, or trigger site, any site, it should bind to it, and it did not destroy the kinase. Kinase is still there. Just its activity is suppressed by binding. Then that drug should be at least to inhibit one kinase, you need to use one drug. In this case, this is breaking, kinase is broken. Once it is broken, then this can be released, and then it can attack another kinase. Then the question is, how can you design this kind of material? Here, this material can be kinase binder. Previously we said kinase inhibitor, they can bind to active site. But this one, any position of a kinase is fine. It's a binding, and the other side, you need to bind to E3 ligase. Then there is a proper linker in between. Then the idea is, if you can find any binding small molecule to kinase, then this part is fixed. Using proper linker, proper E3 binder, this is a fixed one. And you can add any material which can bind to kinase, and this can go into the biological system. It is not just inhibiting the function, it's destroying the kinase. This technique is called as a PROTAP. And the idea was that this was introduced about 20 years ago. At the moment, people did not believe that this can be drug, because this material is a small molecule. Small molecule definition of molecular weight is less than 500. That's the Lipinski rule, right? Rule of 5. Now this is about 500. E3 binder is another 500. If you connect this together, this whole molecule becomes almost 1,000. That's not small molecule anymore. So the size has a severe problem. People did not believe whether this can be real drug. But more and more, they tried to make this smaller and smaller. Now they are entering into the range of less than 500. Now, almost every pharmaceutical company is using this concept, PROTAP-based or protein degradation-based drug development. And very soon, in several years, this technique will get Nobel Prize. Because this is so popular these days. Conventional drug is inhibiting the function of enzymes. But now this drug is actively destroying the target. That name is PROTAP, this inhibitor. Okay? What do you need? You need to have any kind of binder. It doesn't need to be inhibitor. It binds here, that's okay. Still, near to this motif, then anyway, this enzyme will be destroyed. So this is the second approach. There's another approach. Block the synthesis of this kinase. First approach was suppressing the function, right? Second approach, destroying physically. Third approach, do not let the biological system make this kinase. How? That was the Minsk's idea of attacking mRNA. mRNA make protein. mRNA is made by DNA. And if you can suppress somehow this mRNA, it cannot make this kinase. So those idea is also when I was that was introduced when I was a graduate student, like 30 years ago. Idea was utilizing antisense. mRNA is a single strand. If you can get oligonucleotide, like a 10-mer or 12-mer, then it binds to this site. Then this mRNA cannot generate the protein. Ribosome is moving from here to here, it's blocked here, it cannot move forward. Or this dimeric double strand, the mRNAs, is not common in our body, and our body recognizes it as kind of an invading virus. And there's another enzyme, so-called the RNase H, recognize double strand RNA and destroy it. So this is also cutting the message. And don't let the kinase be synthesized. And that technique has been used for some time. The problem was the delivery of this material into the body is highly negatively charged. Putting them into the biological system through the membrane is always difficult. That's why those drugs has been used, like eye drop. Infection to the eye drop, but it's kind of a limited version. So anti-cancer drug is difficult to use. Cancer usually is deep inside. There's the big discovery was made in 2003, almost 20 years ago, so-called double-strand RNA. Double-strand RNA usually is structure of virus. That's why double-strand RNA or DNA is introduced into the body. Then our body recognizes it as a viral infection. And then divide those into two strains. And interestingly, those strains, this is kind of a natural defense system. If this sequence is matching to our mRNA, then it can recognize through this machine, recognize like this, and then seems like it's a cut here and here, regenerate this double-strand RNA. This phenomenon was found, and this is called as a small interfering RNAs, siRNA. Conceptually, this looks like similar to 1분만 네가 설명해 보라면서. With this picture, could you explain those function of siRNA and compare that with the oligonucleotide? 누가 해볼래? 제가 해볼래?
So double-strand RNA enters the cell and it binds to the RISC complex, and then it gets rid of one of the strands of RNA, and then the RISC complex binds to the sense RNA, and then once it's bound, it's cleaved and degraded.
Okay, thank you. So the idea seems like similar to oligo, the antisense. Antisense was if this is an mRNA, then we add only this single strand there, and then you can prevent. Now in this case, binding to this is a cut in the middle, or sometimes you can cut here and here. You can regenerate this double-strand RNA. It can be amplifying this signal, and the effect is much stronger than antisense, the oligonucleotide. So by adding small amount of this double-strand RNA, it has much stronger effect to destroy the mRNAs. So this has been discovered, and then after discovery, within 3 years, it got Nobel Prize. Because that has so high impact. And with this technique, now we have tools. If you know those, we have now the whole genome sequence. We have 25,000 different genes. If you choose, I wanted to delete, knock out one gene, then by designing which part I make copy of this mRNA the sequence 22, 23 more, and then make that double strand, and then in principle you can knock out any of those the genes. Actually, this is not attacking DNA, it's not knockout. It's attacking RNA. If it's not knocked out, then what do you call? Knock down. Okay, suppress those protein synthesis. So this becomes kind of a new the biological tools to control those breaking of mRNAs. So 3 methods I told you. Inhibitor, functional inhibitor, destroying the kinase, proton, and blocking the synthesis of kinase. So these 3 are the most common 3 approaches to block this. Okay, here some other questions. Apoptosis is ongoing, and DNA fragment happens 180. Why specifically 180? It's a good question. Right? So in death of cells, there are 2 kinds of death. Apoptosis is one way. What is the other way of cell death? Necrosis. Okay, Hyungo, can you compare the difference between necrosis and apoptosis?
Apoptosis happens when apoptosis is programmed something. So when cell recognizes this abnormal behavior, it in a way kills the cell. Necrosis happens when some other factor comes from the outside and kills the cell.
Thank you. Necrosis is like a car accident. I didn't mean it. I just crossed the road, and then Yelin was driving, and she saw me. She didn't like me, and she hit me. And I got the damaged and exploded and put everything out. And this necrosis, it can be very toxic to the environment. You may say, oops. And also, toxic material can be spread out. So this is not healthy conditions. So very toxic material like alkylating agent or chemotherapy, those reagents destruct those cells. The cells can be very unhappily die and also pour out all those materials. It can generate inflammations. It can generate a lot of problems. That's necrosis. Not healthy. Apoptosis, in other terms, the programmed cell death. That means I decided to die, or I'm suppressed. Okay, I need to die. Then I write the will, and then I put every materials I have and then give out to the neighbors, and then I become smaller and smaller, shrink and clean them. It does not leave any inflammation behind to give out. Okay, I have the big machines. I decided to give out 1 piece each. You don't want to randomly destroy. You want to cut in regular size. So okay, I have this much of the bidan silk. Then I cut 1, 2, 3, and cut, and then let's spread out. So that's apoptosis. That's why inducing apoptosis is much cleaner way rather than killing those tumor cells by necrosis. So that's why it has some rules why it is under control like this way. And here, double-stranded oligonucleotide. Well, short DNA may be complementary. Double strand, if it's double stranded, it's not complementary, right? Complementary implies it's a single strand. Correct? It can be DNA or it can be RNA. Maybe one of those strands may be complementary, but anyway, siRNA is RNA, double stranded RNA. Divide, and then one strand may bind. Okay, one more thing I want to teach you. You may have heard this, CRISPR. What is CRISPR? Jane, you said.
I've heard of it.
Okay, and what do you know about it? Don't be shy. Okay, cousin of Jenny, Jaeyoon. What is CRISPR? What do you know about CRISPR?
It's a DNA slicing technique.
DNA
Slicing technique.
slicing technique. What is the slicing? What does that mean, slicing?
So you can eliminate very specific parts.
Specific, the eliminating the interpretation. What does that mean, slicing, physically? Slicing 무슨 뜻이야? Slicing is a cutting, right? So CRISPR is a gene editing technique, and sequences specifically, it can find some sequence and then it can click. How does it work? Anybody knows? I will help you with the figure, and anybody can try to explain. Okay, good.
Virus has a certain kind of
나오세요. 숨 없이 누워주세요.
I'm not really sure about it, but virus has some kind of part of the RNA or DNA, and it has a protein named Ras9. I think it was named Ras9, and if there some DNA or RNA comes into the cell, and it is complementary to the preserving DNA or RNA, then it is going to be sliced and break down.
Okay, good try. 성적을 많이 받았으니까. Okay, this was discovered. Okay, that the gene editing technique, you may have heard the name, and it's slicing some specific gene sequences on our DNA. It's very powerful. The discovery of this, it was discovered in bacteria. In bacteria, there was a funny repeating sequences were found. This is identical part, and then in between, there are some fragment of genes are inserted there. In the beginning, it was not clear what it means. And later, it was found that these sequences here, they are virus sequences. And it raised the curiosity for some biologists, and then they tried to understand what does that mean, why bacteria has a virus sequences. And later they found that this is part of virus sequences, and then this constant sequence is binding to some enzyme recognition site, and then as a the result, this enzyme can cleave this bacteria generate this kind of a complex RNAs. And this part is the virus RNA. And they found the acting enzyme for this called Cas9. Cas9 recognized this part and then bind to it. And then this is the virus specific sequence. And when the virus comes in, if that virus has this sequence, and then it recognizes this virus sequence and slice, as James said. So this is bacteria's defense system, sequence specific defense system, not like a secreting antibiotic or antiviral. This is very sophisticated immune system. Our immune system, we mainly utilize antibody. Antibody is based on protein, and protein recognizing those shape of the enemies. This bacteria, they recognize the DNA sequence of virus. In many cases, virus bacteria, when they compete, virus wins. Somehow virus is life or not is debatable, but still, virus infection is very fatal in many cases, not only to us, and even to the bacteria. Bacteria, most likely, they lose the battle, they die out. If they survive, they save small fragment of virus in their body and then deposit into their genome. If you meet my babies, if you meet this virus again, you cut it, utilizing this system. That was the discovery of a CRISPR system. And then some scientists, they realized that the potential of this technique. And then using this technique, now the whole idea is utilizing Cas9. Cas9 is a bacterial protein. And then which can recognize this part and then bind to this. And then any double-strand DNA can be recognized. And one of them is recognized like this and then cut it. siRNA, the target was a mRNA, right? That was a knockdown. In this technique, this can modify double-strand DNA. It can be knocked out. Genetic modification is possible utilizing this technique. And now this one is right now, it's a two-strand, it's a little inconvenient. And they changed this into a single strand. So make connection here, and the whole structure is connected. Then to do that, what you need is DNA sequence of this. This part is the constant part, which can be recognized by Cas9. And then this is your target gene sequence. So this single strand RNA is called as sgRNA, single strand guide RNA. Then this part is a constant. You can choose your target sequence. And cleavage site is also known. From here, 1, 2, 3, 4 position will be cleaved. Then, what you need is you put Cas-RNA into the cell. And this RNA, sgRNA together, then it goes into the cell, any cells, bacteria, our cells, mammalian cells, it goes in and then cleave that DNA in both sides. Effectively knock out one gene's information. This is the major principle of CRISPR. With this technique, it's surprisingly simple. By putting just one enzyme gene, or you can even inject Cas-RNA, the protein, Cas9 protein, and just RNA. Then you can selectively cut any gene you want. So this is the power of gene editing. Actually, this is also third generation of gene editing. This kind of the development has been completed over 20-30 years. The first one was the zinc finger technique, which can recognize DNA sequence by protein, so-called zinc finger. Zinc binding protein which has this shape, and then it can recognize some part of the DNA sequences. But that was not perfect to cover all the sequences. That was the first generation. Second generation, TALEN, T-A-L-E-N. That has been, people believe that that's a new revolution to replace each single nucleotide we can recognize. After this, CRISPR is discovered. All the techniques become history. So powerful, and as you know, it got the Nobel Prize within several years. Now, this is one way you can delete those information for your target. If it's a kinase, then you can design the kinase sequence here. You can deliver it, and you can modify it permanently. And this technique has been used in China to modify embryos, the gene, to make that the baby is HIV resistant by removing HIV infection receptor. So in principle, seems like this technique can be used for changing human gene too. Now, a little modified version of this. This is also very powerful. I want to introduce. Original CRISPR is a cutting. Now, intentionally, you can deactivate those Cas9. It can bind to it, but it blocks the cutting. That's a D-Cas9, deactivate the Cas9. Here, this one, if this is binding to promoter area, you can add activating motif here. Then, this is your DNA, and then this is a promoter area. It starts to make an mRNA. Activating specific genes transcription is possible. That's CRISPR-A. Exactly the same way, you can add the inhibitor motif here, then you can block that RNA synthesis, CRISPR inhibition, CRISPR-I. So this is an effective way to control those mRNA synthesis, activating or inhibiting. It can be effective knock up or knock down. Original CRISPR was a knock out, right? Cleave off. But it can be used as express further or suppress those gene expressions. So this is kind of cutting edge the technique in gene regulations. So one part of blocking or activating your target proteins. Okay, so this is the summary of it, and I think this is the last page of today. Okay, so today we covered about second generation of anti-cancer drug in terms of targeted cancer therapy. Next week we are moving to immunotherapy and also cell therapy for the cancers. Now we have only 4 lectures left over. Third generation of cancer, aging and anti-aging, and optics and spectroscopy, and probe and imaging. You have only 4 chances. If you wanted to present something, it's better to volunteer now. Okay, you can send me a call or email if you want to have a 5-10 minutes small presentation. You volunteer. Okay.